Asynchronous programming in JavaScript. Imagine a busy kitchen, where chefs prepare multiple dishes at once. This analogy perfectly illustrates asynchronous programming in JavaScript. First, let's understand the fundamentals of asynchronous programming. Asynchronous operations allow JavaScript to perform tasks without waiting for one task to finish before starting another. This enables responsiveness and improves performance in web applications. Callbacks are the foundation of asynchronous programming in JavaScript. They allow us to specify what should happen after an asynchronous task completes. However, Callback Hell can make code difficult to read and maintain. Let's dive into a practical example of callbacks. This code demonstrates a simple callback function named greet, which takes two parameters: name a string and call back a function. Inside the greet function, a greeting message is logged to the console, followed by the execution of the callback function. When calling the greet function with the name nerdy code crafter and a callback function, the greeting message is logged first, and then the callback function is executed. Callbacks are vital for asynchronous programming in JavaScript. They enable code execution asynchronously, avoiding waiting periods. Callbacks specify actions post-asynchronous task completion. They're commonly used for tasks like data fetching and event handling. Understanding callbacks is crucial for responsive web app development. This code simulates an asynchronous HTTP request using setTimeout. Once the data is retrieved, the callback function passed as an argument is executed. In this example, process data is passed as the callback function to handle the fetched data. The usage demonstrates calling fetch data and passing process data as a callback to handle the data. Callback hell is when multiple asynchronous operations are nested, leading to messy and hard-to-read code. It makes code maintenance and debugging difficult due to excessive nesting. Managing asynchronous control flow becomes challenging. This often happens with complex tasks like handling multiple HTTP requests. To avoid callback hell, consider using alternative approaches like promises or async await. This code snippet illustrates callback hell, where nested callbacks handle asynchronous tasks. Each async function represents an asynchronous operation needing a callback for completion. The nested structure makes the code hard to read and maintain, worsening with more nested callbacks. Managing asynchronous control flow becomes challenging with nested callbacks. Deeper nesting makes code harder to read and maintain. More callbacks increase the risk of errors and bugs. Limited scalability with growing code complexity. Large codebases may encounter callback hell, hindering organization and debugging. This code showcases callback-based error handling in asynchronous programming. The async function accepts a callback function with two parameters: an error object and data the retrieved data. Inside the callback, we check if an error occurred is truthy, logging the error if present, or else logging the retrieved data. However, this approach can become cumbersome and error-prone, particularly in complex asynchronous scenarios. Promises offer a structured approach to handling asynchronous operations. They provide a cleaner alternative to nested callbacks, reducing the risk of callback hell. Promises represent a future value or error that will be available asynchronously. They simplify error handling by incorporating built-in support for rejection and chaining. Promises usher in modern asynchronous JavaScript programming practices. This code demonstrates how to create and consume a promise in JavaScript. The promise constructor takes a function with two parameters: resolve to fulfill the promise and reject to reject the promise. Inside the promise, execute a function, an asynchronous operation. For example, fetching data from a server is performed. If the operation is successful, the promise is resolved with the fetched data using the resolve function. Otherwise, it's rejected with an error using the reject function. The then method is used to handle the fulfillment of the promise, and the catch method is used to handle any errors. Promises represent the eventual completion or failure of an asynchronous operation. They exist in three states: pending, fulfilled, or rejected. To create a promise, we use the new promise constructor, passing an executor function. The executor function has two parameters: resolve to fulfill the promise and reject to reject the promise. Once settled, a promise remains in its final state, providing a structured approach to handling asynchronous operations. This code demonstrates the structure of a promise, including the creation of a promise using the promise constructor, and the execution of an asynchronous operation inside the promise executor function. Depending on the outcome of the asynchronous operation, in this case, generating a random number, the promise is either resolved with the result or rejected with an error message. The then method is used to handle the fulfillment of the promise, and the catch method is used to handle any errors. Promises can be chained together to handle sequential asynchronous operations. Each then method in the chain returns a new promise, allowing for continuation of the chain. Chaining promises leads to more readable and maintainable asynchronous code. Errors can be caught and handled using catch at any point in the chain. Chaining promises facilitates the composition of complex asynchronous workflows. In this code, we chain promises to handle sequential asynchronous operations. We define fetch data to simulate fetching data asynchronously and process data to process the fetched data. Chaining promises, which then allows us to handle each operation sequentially. The first then logs fetched data and returns a new promise after processing. The second then logs processed data. Catch handles any errors. This chaining makes our code more readable and maintainable. Error handling with promises is crucial for robust asynchronous programming. Promises offer built-in error handling through the catch method. Errors within a promise chain can be caught and handled using catch. Appending catch to the end of a promise chain allows for comprehensive error handling. Proper error handling enhances code reliability and maintainability. In this code, we're demonstrating error handling with promises. We start by defining a fetch data function that simulates an asynchronous operation. Inside this function, we create a promise that resolves with some data after a simulated delay of 1 second. We then chain promises using then to handle the resolved data in the first then handler. We log the resolved data to the console and process it by converting it to uppercase. This demonstrates a successful operation. Next, in the second then handler, we log the processed data to the console. This completes our promise chain, and everything works as expected. Now, let's consider error handling. If an error occurs during any part of the promise chain, it will be caught and handled by the catch method. We've set up a catch handler at the end of the chain to log any errors to the console. Even though we've simulated successful operations in this code, the error handling mechanism is in place to handle any potential errors that may occur during asynchronous operations. This ensures that our code remains robust and reliable. Async, or await, is a modern approach to asynchronous programming in JavaScript. It allows us to write asynchronous code in a more synchronous-like manner, simplifying the process of working with promises. With async, or await, we declare async functions using the async keyword, and use the await keyword to pause execution until a promise is resolved. This improves error handling, readability, and overall code maintainability. The fetch data function is declared with the async keyword, making it an async function. Inside fetch data, we use the await keyword to pause execution until the data is fetched from the API asynchronously. The await keyword allows us to write asynchronous code in a more synchronous-like manner, improving readability and maintainability. In async functions, we declare asynchronous operations using the async keyword. Inside these functions, we can use the await keyword to pause execution until a promise is resolved. This allows us to write asynchronous code in a more synchronous-like manner, improving readability and maintainability. The await keyword can only be used inside async functions. By utilizing async, or await, we simplify the handling of asynchronous operations, making our code more intuitive and easier to understand. Inside the async function fetch data, we use the await keyword to pause execution until the data is fetched from the API. We use a try catch block to handle any errors that may occur during the asynchronous operation. If an error occurs, for example, network error or invalid response, it will be caught and logged to the console. Let's dive into an example demonstrating the power of async, await in fetching data from an API asynchronously. We'll define an async function called getData to handle the data retrieval process. Inside the getData function, we utilize the await keyword to pause execution until the data is successfully fetched from the API. Once the data is retrieved, we return it, allowing further processing if needed. By leveraging async, await, our code becomes more streamlined, readable, and intuitive, simplifying the asynchronous workflow. We define an async function fetchData to fetch data from an API asynchronously. Inside getData, we call fetchData using the await keyword to pause execution until the data is fetched. If fetching data is successful, it's logged to the console. Otherwise, any errors are caught and logged. In async await, error handling is streamlined with the use of try catch blocks. We can wrap asynchronous operations inside try blocks and catch any errors that occur. If an error occurs during the execution of an async function, it's automatically converted into a rejected promise. This simplifies error handling, allowing us to handle errors in a more synchronous-like manner. By utilizing try-catch blocks, we can effectively manage errors and ensure the robustness of our asynchronous code. Inside the async function fetchData, we use a try-catch block to handle errors that may occur during the asynchronous operation. If an error occurs during fetching, for example, network error or invalid response, we throw a new error with a descriptive message. Let's explore some best practices when working with async, await in JavaScript. Avoid mixing async, await with promise chaining to maintain code consistency and readability. Utilize async, await for multiple asynchronous operations that depend on each other, improving code structure and clarity. Ensure proper error handling within async functions using try-catch blocks to catch and handle any errors that may occur during asynchronous operations. Keep async functions concise and focused on a single task to enhance code readability and maintainability. These best practices help optimize the use of async await, resulting in cleaner and more maintainable asynchronous code. Avoid mixing async, await with promise chaining to maintain code consistency and readability. Use async, await for multiple asynchronous operations that depend on each other to simplify code structure. Ensure proper error handling within async functions using try-catch blocks to catch and handle any errors that may occur during asynchronous operations. Congratulations on mastering Asynchronous JavaScript programming essentials. Keep practicing to reinforce your skills. Please subscribe to my channel. Thanks for watching. Happy coding!